All right, looks like I'm recording the screen, and I'm going to cover chapter 4. It is for system resultants. And we're going to introduce the concept of moment. We'll be talking about cross products, things that you may be familiar with from other classes. Anyway, so if I have a force acting offset from a possible axis of revolution, then the effect of that offset force is to induce rotation. And the effect of the force will depend, of course, the magnitude of the force um, and the distance measured from the axis of rotation to the line of action of the force. So for a given force F, maximum effect is when, holds to reason, when this angle is 90 degrees. If that angle is other than 90 degrees, the effect is less. You can see here there's distance between the line of action of the force and the axis of rotation that is less. The sign of theta makes it less than d. And of course, the minimum effect, I have it when I'm pulling the axis. The arm of the force is going, the moment arm, it's 0. Okay, so we have moment of a force, sometimes torque, but moment is used the more general meaning. And we're going to define the moment magnitude as the product between the force and the distance from the point or from the axis of rotation to the line of action of the force. So observe this figure as a top view. So I have the force can act anywhere along its line of action. This is the distance from the axis of rotation from the point. And the magnitude of the moment is going to be this product F times D. Units are Newton meters, pound foot, and of course could be others. Moments are vectors, and they have direction and orientation. The direction of the moment is perpendicular to the arm of the force in the force itself, or has direction of the axis of rotation, the axis of the moment axis. And we define them using the right-hand rule or right-hand screw. So right-hand rule, you grab the axis, you point the fingers in the direction of the force, and the thumb points in the direction of the moment. Of course, the axis itself can be oriented, so moments could be either positive or negative. Okay. In general, we can have more than one force inducing rotation to a rigid body, each with their own moment arm. So the resultant moment is going to be, again, the moments of the individual forces are valued about the same point, or about the same axis, would be z-axis in this two-dimensional case. And the resultant moment is the sum of moments of the individual forces, right? And likewise can be, oriented, right-hand rule. So it's algebraic sum, but some moments are positive, some are negative, clearly. Okay, there are some examples here on how to evaluate the moments of some forces given some geometry. So really, it's a matter of finding that distance or moment arm. Okay, the most general way of or defining moments of a force is about a point is by using the cross product. So this is introduced here as a mathematical concept, and then apply to the definition of moment. So if I have two vectors, then the cross product A cross B, this notation, will result in a vector C. The magnitude of the C, of the cross product, will be the magnitudes of A times magnitude of B times the angle between the two vectors, measured from A to B on the shortest path. Okay, and in terms of orientation of the cross product C vector, that's going to be perpendicular to the plane formed by A and B, and has a direction according to the right-hand rule. So you rotate A towards B. Okay, so it's shown here. So I have vector A that I crossed with B. I'm taking the angle between A and B on the shortest path, and right-hand rule, I'm going the direction of from A to B, that is, and I get the orientation of the unit vector associated with the cross product, UC. Okay, and some properties of cross products. They're not commutative, so A cross B is not B cross A. Rather, A cross B is negative B cross A. If we multiply with a scalar, that's associative, so I can take A and multiply just vector A. I can take A, multiply just vector B, and then do the cross product. Or I'll multiply the scalar to the left or to the right. So I evaluate cross product and then multiply by that constant. And then we have the distributive law. So A crossed by the sum of A plus B. I cross A with B. I add the cross product of A and D, and get the same result. Cartesian vector formulation using determinant notation. So in expliciting the components of the individual vectors A, B in the cross product, I'm using unit vectors I, j, and k associated with the three axes. And so essentially resolving the vectors A, B and their x, y, z components. So I'm going to make use of, or at some point it will occur, these cross products between the unit vectors. So we're going to use the distributive law, again, splitting A and B into their individual components. And this results will intervene. So I crossed with J, it's positive K. I crossed with K, I go A to K, that's negative J, and so forth. And then if the vectors are parallel, their cross product is 0. Sine of 0 is 0. All right, so I crossed with I, J crossed with J, or K crossed with K, they are all 0. But we're not going to go through these steps because they are easy way to state cross products, keeping track of these multiplication. Again, using the distributive law. So I have vector A explained as, or resolve into x, y, and z components, likewise with B. And then I'm doing the multiplication, and so on. Take here, like this would be 0, this is 0, this is 0, and then based on the earlier table, I replace the effect of crossing the cross unit vector parts. Anyway, these can be cast in a determinant form. So A cross B, I have these unit vectors I, j, k, first line. Second line, the scalar components of A, and third line, scalar components of B. And then if I want to get the IJK components of the cross product, I expanded the determinant about the first row. So I, and then will be the minor. So I have I unit vector times would be a y times bz minus az times by. These are products between scalars. And then j, this is 1, 1, this is 1, 2, so it'll be negative. So negative j, and then I have ax bz minus az bx plus k unit vector times ax by minus ay bx. All right, everything else is, or these are explained here again, expansion by of the determinant about its first row. And remember the negative sign here. Why is that? Because I have index 1, 1, 1, 2. So 1 plus 1 is even, 1 plus 2 is odd, 1 plus 3 is even again. So if the indices added are odd, then this will be negative. Irrespective. So if I could expand the determinant by any row or column. But there will be some terms that have negative, and the reason is or keeping track of those is the way I explained. Okay, moment of force, moment of a force vector formulation is a cross products. So I have here the position vector of any point on the line of action of the force. Really, so I can have the force show, like could be the tail of the force vector, but the force vector can be anywhere along its line of action. It's a sliding vector. By the way, forces are sliding vectors. So as I'm sliding the force along its line of action, this radius changes, but the cross product remains the same. Anyway, applying the definition. So I measure, again, I'm crossing R with F. So I need to, here they are head to tail, but I slide R to where I can measure that angle to get it into this, what was it? Cross product, this arrangement, right? So A is R, B is the force. So I was sliding R to where they are tail to tail. Right? So, and then you measure the angle between R and F as you place them tail to tail, and you measure. This is an oriented angle. I don't know why they show a double arrow. So it goes from R to F, and that angle, it's given also the direction of the moment, or you use the right-hand rule. Okay, so the magnitude of the cross product is FR times sine of theta, and then the moment axis, that unit vector. But how we're going to making use of the cross product, how is that going to help us simplify our analysis? Okay, so the first thing that it's explained here is that the one that I was telling you. So I can slide the force along its line of action, and that will change the position vector R, but the result is the same because of the this distributed or rather principle of transmissibility of a force. So force is a sliding vector, has the same effect anywhere along its line of action. All right, so really we will choose the position vector of the force the most convenient way, or based on what information is given for a problem at hand. Okay, so Cartesian vector formulation of a cross product using determinants. And um, looking at this figure, it shows a force, and we have its fx, fy, fz components, although this will be the second term, the cross product. And then we position a point on the line of action of the force with Rx, Ry, Rz. And the moment, which is R crossed with F, will be a vector that is perpendicular on the plane formed by the vector R and a vector F, and has the direction of going from R to F. Well, for that we need to slide R to where tails match, so R towards F on the shortest path, and that's the direction of M. Okay, the force vector can be resolved in its well, it is here resolved in its x, y, and z components. And as we expanded this determinant by the first row was minor, so I, R, Y, F, Z, negative R, Z, F, Y, right? The okay, so the idea here is that you can work with like, instead of having this single force, you have three of them. So you substitute the original vector force with its fx, fx, fy, and fz components, and is like adding the since R is common to the three components, they share a tail. It's like setting R crossed with the fx, R crossed with fy, and R crossed with fz, and you add them together. Okay, so yeah, that might be of some convenience, and it's really the principle of moments here, Varigno's theorem. And Varigno's theorem, it's presented here for the two-dimensional case, but can be extended to 3 dimensions. So we have and can be other than orthogonal components, really. So I can get the force vector resolved into two components about two directions, in particular orthogonal. So the moment of the initial force is the sum of moments of the two components. And that may be, in some cases, may be easier to find the arm of so instead of looking for the arm of the initial force, the arm of the x-axis component would just be this distance y, and the arm of the fy components will be this distance x. And I could, again, 90-degree angles between the arm and the force, and it might be easier to, or oftentimes it's easier to work this approach. All right, so yeah, we covered the theory essential for working with forces offset from a point about which they induce rotation, and there will be a number of problems that we're going to cover from the end of the chapter. These two sample problems are relevant to follow. There are several approaches to evaluate the moment of a force. So either getting the arm of the force, resolving the force in x and y components, or resolving a force in a direction that is through the point about which rotation is induced in one perpendicular to it. And another example again of this, the same uh, nature. Again, you can evaluate directly. It might be the most difficult approach to evaluate the arm of the moment, distance between the point of rotation and the line of action of the force. Work with Varignon theorem. So resolve the force into x and y components, evaluate the moments about the O point or z axis of the individual x and y components. They may have different sign, you add them. Or the third one is to find the component of the force perpendicular to an arm that is given in the direction, or through rather the uh, point about rotation is expected or evaluated. Anyway, so this was it. I'm going to stop recording and thank you for watching.